Hi, everyone. All right. Give people about one more minute to sign on. Um, the first slide here, just a couple reminders. Lab 10 is out, and after today's lecture, you'll have everything you need to finish it. Homework 9 is due next week. Um, we also wanted to put up an advertisement for the Spring Majors Forum, which is going to be held online tomorrow. Unfortunately, we can't give out pizza, which was one of the main draws of this. But if you have any questions about the major, if you're a current major or thinking about majoring, so it'll be me and the other director of undergraduate studies. There'll also be Leila Davachi will be on there, who's going to be running the honors program for next year. So if you're interested if you have questions about the psych honors program, that would also be a good time to come. Um, I'll also be answering questions about people interested in research. So yeah, please join us if you're available tomorrow if you have any questions. Okay, so today we're going to talk about the very last kind of null hypothesis test. This is called an analysis of variance test, which is abbreviated ANOVA. And so the motivation for talking about this last test, we've first started thinking about one sample tests. So, for example, a one sample t-test where we're comparing a single population of people to some kind of null hypothesis, which is maybe 0 or some other kind of baseline. Then we talked about two sample tests, right? These independent two sample tests where we have two independent groups. So we're measuring values from two different groups of people, and we want to test whether their means are the same or not. And so we might think about how we could generalize this to more complicated kinds of experimental designs. So, for example, what if instead of two groups, we have 3 or 4 or more, right? We might not just be comparing like an intervention versus no intervention, but maybe there's different kinds of interventions we're trying. Maybe we're interested in different types in categorizing people different ways. So maybe we could label people with different types of group labels, and we want to figure out which of those labelings is most interesting. And so for the one sample and two sample tests, we talked about those for things like t-tests or some of the non-parametric rank tests. But in general, for these more complicated tests where we have more than two groups, these all go into this new framework, which is what we're going to talk about today. And so this new framework is built around thinking about sums of squares. So we've computed sums of square deviations a lot of times in the class. So for example, if we want to compute the variance within some data set, we just need to know the mean of that data set. We compute all of the deviations away from that mean, and then sum up the squares of those deviations, right? And so this tells us something about how much variability there is around the mean, right? It's a way we can get a measure of dispersion. And this is actually a really general idea, right? That if we can sort of keep track of the deviations in our data. So if we can try to explain why different groups, for example, might have different means, then we can use this as a way to try to figure out where the differences in our data are coming from. So the idea is if we just have all of our data set, our whole data set, these deviations tell us about how much variability there is among the different people in our data set. And we want to figure out, can we break down this data set into groups that have smaller deviations, right? So for example, we could compute the sum of squared deviations inside each group. And that gives us a measure of how much variability there is inside each of these groups, which we can then compare to the variability that's across all of the groups. And so the idea is that we're going to compare to what extent is these deviations in the data, are they explainable by these group labels? To what extent can we explain the variability in our data by breaking people down into these groups? And so the key idea here, especially for the first version of the ANOVA we're going to talk about, is that the variability in our data, the total variability in our data, can be broken down into a within group variability and a between group variability. And comparing these two sources of variability is going to be the way we're going to set up this ANOVA test. So let's just do a cartoon example of this. So you can imagine we have a bunch of data. So we have one measurement in each person. These measurements are ranging from like 7 to 20 in this example. And right now we are just looking at this scale measurement that we're getting. We're getting this one measurement for each person. And so something we could compute here is we could compute the overall mean. We're going to call, in the context of ANOVAs, we're going to call this overall mean the grand mean, which just means that it's an average over every single person in the data set. And we can then compute the total sum of squared deviations from this mean. So for every person, we just measure how far away they are from this mean, and we could sum up the squares of all of these line lengths. Right, this is just the way that we compute the variance, right, way back near the beginning of the class, right? All we're doing here is computing an overall mean, and we can measure the squared deviations from that mean. Okay, so this total sum of squares is telling us something about how much overall variation there is in our data, how much dispersion there is, right? On average, how far away from the mean are each of these points. Okay, so now we can start to break down this total sum of squares. And so now we can imagine that for each person, we also have some kind of nominal group label for each person, right? So here there's like 3 different levels of this single nominal factor. There's green and red and blue. And so just by eye looking at these, right, it seems like these groups are kind of separated, right? Meaning that there's some relationship between whatever this scale measurement is that we're getting and the group label. And so what we can measure here is we can compute a mean inside each of these groups, right? So we can compute a blue mean, a red mean, and a green mean separately for each of these 3 groups. And then we can compute this same kind of sum of squares measure, but inside each of these groups. So for every group, we're going to take a person in that group and look at the deviation to their group specific mean. So you can see all the blue points here, we're measuring deviations from the blue mean. All the red points, we're measuring deviations from the red mean, right? We're measuring the same exact sum of squares that we were before, but now we're doing it inside each of these groups and using their group specific mean, right? The grand mean is not involved in this calculation at all. So this is the within group sum of squares that's telling us how much variability there is inside each of the groups. And the kind of complement to this is the between group sum of squares, which is that if we ignore this within group variability and just look at the group means, we can get this between group sum of squares, which is basically just asking how far are these means from the grand mean, right? So for every point here, we could just like imagine we're getting rid of the within group variability. So we're just pretending that all of the blue points here are all exactly the blue mean, and same for the red and the greens. And if that's true, the question is how much sum of squares variability is there still left in the data, even after taking out this within group variance. So if we collapse all of the participants to their within group means and then compute this overall sum of squares, this is what we call the between group sum of squares. It's a sum of squares that's coming just from the fact that these groups have different means. And so we can think about this as what we'd call a hierarchical model in stats, meaning that there's some overall amount of uncertainty in our data, which is this just total sum of squares that we computed first. And this variability is coming from 2 different sources, right? One source is this within group variability. And so we could imagine, right, within each group, there's some uncertainty even among all the people that are labeled as group A. And if we, so that's one source of variability. And if we got rid of that variability, then all of the points within group A are all gonna be exactly at the mean of that group. And then a second source of variability is that different groups have different means. And so this first thing is the SS within, which is how much variation is there inside group A and group B and group C. We would just like sum those up. And then SS between is how much variability is there among the group means versus this grand mean. And the key fact about why all this works is that this total sum of squares that we started with is just a linear sum of the within group sum of squares and the between group sum of squares. Right, so what we're doing is we're taking this overall amount of variability in our data and we're splitting it into two different quantities. One that's telling us how much variation is there in the means of each group, and the other one is telling us how much variation is there inside each of these groups. And so this is going to be the key tool we're going to use for building these ANOVA tests. Okay, we'll do our first quiz. Again, don't respond in the chat until the timer has counted down from 15. All right, the question is, when we're breaking down this total sum of squares, what are the two quantities we're going to break it into? Within subject and between subject sum of squares, grand means and group means, within group and between group sum of squares, or one sample and two sample sums of squares. All right, what do people think? All right, I'm seeing C's, which is good. So this is the main idea for ANOVAs is we're going to take this total sum of squares and break it into a within group sum of squares that tells us how much variation there is inside each of the groups, and a between group sum of squares. We're not actually there is actually a within subject and between subject version of ANOVA, which we'll talk about on Tuesday, but we're not talking about that today. Okay, so let's just look at mathematically how we compute this. So we want to be able to figure out how to compute all three of these things: the total sum of squares, the within group sum of squares, and the between group sum of squares. So the total sum of squares, again, we've basically done this before when we're computing variances. All we do is we compute the grand mean, which is this x bar g. And then we are going to take our data minus the grand mean. That gives us all of our deviations, one for each data point. And then we're going to square up and sum these deviations. If you're doing this by hand, there's also a slightly easier way to do this, that you don't actually have to compute the deviations ahead of time. If you just take the sum of the squares of all the data and then subtract out n times the grand mean squared. These are both the same equation. The bottom one just is sort of like one fewer step if you're doing it by hand, right? But I think that the top one is the more intuitive way to think about this, which is that we're measuring for every data point, how far away is it from the mean? So if all of our data points are exactly the mean, then that would mean that there's the total sum of squares here would be 0. There's no variation in our data set, and there's nothing sort of interesting that we could possibly say. Right? What we're hoping is that there is some variability in our data set here that we're going to try to explain. Okay, so then another thing we need is the between group sum of squares, right? And so remember, this is the term that's telling us how far apart are the different groups from each other. And so this is relatively easy to compute. You have to just be a little careful with this summation here. This is not a summation over the data points. Right here, we're summing this I that we're summing over is the groups. So if we have k different groups, what we're going to do for each group is take the mean of that group, see how far away it is from the grand mean, square up that difference, and then multiply by the number of points in that group. Right, so this is a summation over all the groups. For every group, we're measuring what's the square deviation from the grand mean, and then we're just weighting by the number of points in that group. In many but not all cases, these ends, we're going to try to design our experiment so these ends are the same across group, but they don't necessarily have to be. Okay, so this is also not that hard to compute, right? It just has k terms in it. This summation, there's one term for each group. And usually the number of groups k here is going to be relatively small. This is just the number of levels of whatever nominal factor we're using to label these groups. Okay, so then the last thing we need to compute is this within group sum of squares. And so this is a little more complicated because what we're going to have to do is inside every group, we're going to have to measure the squared deviations from the mean inside that group. So if we want to write this out, it'll look like this, right? So there's an outer sum here. The first sum is this sum across groups, right? So what we're saying is for every group, we are then going to look at every point inside that group. So this summation here is over all the points inside group I. And so for every point inside group I, we're going to measure the deviation of that point from the mean of group I and sum up the squares of these things. And then we're going to repeat that across groups. Right, so the notation here is slightly clunky, right? But all we're doing is for every point so for each group, we look at the deviations of every point from the mean of that group. So another nice thing here though is we actually don't have to do this because, right, remember the total sum of squares is divided up into the between and within. And so since this is kind of the most annoying one to calculate, usually we don't calculate this one, right? We just calculate the total sum of squares, right? Which is that sum over all the points, how far away they are from the grand mean, right? So we compute this thing, which is the total sum of squares. So this, there's a term in here, one term for every point, right? We see how far away every point is from the grand mean. This is just ignoring the group labels entirely. Then we compute this thing, which is, this requires just computing a mean for each group, that these are the x bar sub i's as the mean inside each group. How far away are those from the grand mean? And then this last thing, we can compute just by subtraction, right? That once we know the total and we know the between group, whatever's left over that's not the between group stuff is the within group stuff. Again, you could calculate it out with this formula. It's not that hard, but there's no need to. Okay, I'll do another quiz here. So when we're computing these sum of square terms, which one is the easiest to calculate? Meaning it has the fewest terms in the summation that we have to compute. The total sum of squares, between group, within group, or they're all equally hard. All right, I put your answer into the chat. Which one, right, if we only wanted to do one of these, which would be the easiest one for us to do in terms of, it requires summing up the fewest things. Okay, I'm seeing a lot of A's, and so A is the maybe second closest answer here, right? So the total sum of squares is this, right? And so this is relatively easy to calculate in the sense that we just need a grand mean. We're computing the deviations from that mean, but this summation here is over every single data point, right? We need to, for every single data point, we need to compute how far away it is from the grand mean. Right, whereas when we're computing this between group sum of squares thing, this, at least assuming we know what these group means are, these x sub I things, this actually has fewer terms in it, right? This is we only need to sum up this sum is just over the number of groups, okay? So, this is a little bit of a cheat because to compute these group means, usually you're going to have to look at every data point also, right? But at least this formula here is really easy, right? Like in our example, there'd only be three terms in this, right? Which is, right, this between group sum of squares. All you're doing is just figuring out how far is this blue thing from the mean, how far is this red thing, how far is this green thing. There's only three numbers in that sum, right? Whereas the total sum of squares is you have one of these for each point, right? The total sum of squares requires for every point we have to measure a squared deviation to the grand mean. So it's definitely the case that the within group is the hardest, right? The within group requires doing that weird double summation. But at least if you have the group means, the between group sum of squares is really easy to calculate. It's just the sum over the squared deviations of those means, those group means from the total. Okay. If anyone has any questions about that, feel free to answer. Okay. Okay, so all right, so what are we going to do with these sums of squares? So today's lecture is talking about analysis of variance, right? This is what ANOVA stands for, is variance. And so to actually do this test, we're going to have to put these sums of squares into something that looks more like a variance. So if you remember, to compute a variance from the total sum of squares, we have to divide by something, right? And in order to get a variance measure that actually is a good estimator of the population variance, we talked way back when that the right denominator here is n-1, right? The number of data points minus 1. And so now we're thinking about this in a slightly different way, that this n-1, the denominator, is the degrees of freedom for a variance. So again, this is the same formula that we saw back in like week 2 of the class. Right, to get a variance, what we're doing is summing up the squares of all these deviations and then dividing by n-1. Right, so we kind of need to do some kind of normalization here, because the sum of squares is just going to get bigger and bigger as our data set gets bigger. By dividing by n-1, we now have a variance that's it's in like squared units of whatever we're originally measuring. So we're now gonna start defining some new quantities here that are kind of like variances. They're gonna have a very similar form, where we're gonna take a sum of squared deviations and divide by degrees of freedom. But they're not exactly gonna be variances, and so we're gonna call these things mean squared deviations, or just mean squares, right? And what this means is that if we take a sum of squares and then divide by some kind of degrees of freedom, which are usually going to be related to the number of data points, this is going to give us a mean of those sum of squares. So we're going to call these mean squared deviations, right? And again, these things are kind of like variances. They're a sum of squared deviations divided by a degrees of freedom, just like the variance is. Okay, so we can take our sum of squares, our between and within sum of squares that we just talked about how to define, and we can compute these mean square versions of them. So for our between group sum of squares, we're going to take this SS between, which remember is the sum over these k groups of how far away is the group mean from the grand mean. So we take the sum of squares, and then we divide by the degrees of freedom for this between group measure, which is k minus 1. And remember, k here is the number of levels, right? The number of groups that are defined by this single nominal factor. We also can define a within group version of this. So this is our mean squares within, is we take the sum of squares within measure and divide by the degrees of freedom, which in this case is the total number of subjects minus the number of levels. This degrees of freedom here is not super intuitive. It's kind of like the total number of degrees of freedom here. Right, so what these equations are doing is they're just a way of kind of normalizing the sums of squares that we're getting and turning them into these mean square quantities instead. Okay, so we're almost there to a statistical test here. And so it turns out these mean square things we've computed are the kind of right statistic for doing our ANOVA hypothesis test. And so the way we're going to run this ANOVA test is that if the null hypothesis is true, then the mean square between group should be about the same as the mean squares within group. Right, so this is going to be our null hypothesis that this ratio of mean squares between to mean squares within is going to be about equal to 1 if the null hypothesis is true. And the null hypothesis that we're going to test here, at least the first kind of null hypothesis we're going to test with this, is just to test whether these group labels have any meaningful relationship to the thing that we're actually measuring. So if these group measurements that we're making, these measurements we're making are related to our group labels, then what we should see is that there should be a lot more difference between the groups than within the groups. If a group label is 100% predictive of exactly what response people are going to give, then this MS within should be 0, right? There should be no variability once we know which group you're in. Whereas this MS between should be large, which is the difference between the groups, right? So what we're measuring here is how far apart are the groups from the grand mean compared to how much variability is there inside every group. And so if the groups are meaningless, then these two numbers should be about the same, that the variability between the groups and within the group should be about the same because the groups don't actually mean anything. If the groups are really informative about, and so what we're going to do here is we're going to compute these two values, and we're going to see if this ratio is significantly bigger than 1 or not. And so the nice thing about this somewhat complicated setup is that this works for any number of groups, right? So this way we set this up, we're just assuming that we have some kind of categorical label for each person. And it doesn't actually matter how many levels there are, right? There could be many groups here. There could be dozens of groups, right? And we can still compute these within and between measurements. So, anytime we're doing null hypothesis testing, right, what we need to figure out is what is going to be a sort of interesting deviation from the null, right? This is even if the null is true, this ratio is not going to be exactly 1. So we need to know what the null sampling distribution is, right? How big does this ratio tend to get if there really is no interesting meaning to the group labels? And so this sampling distribution is called the F distribution, named after Fisher. And this F is just this ratio that we were just describing. How big is the between subject mean squares compared to the, between group mean squares compared to the within group mean squares. And so if the null hypothesis is true, then this statistic is going to come from an F distribution. And so just like the logic of all our hypothesis tests here, right, we're going to, we want to figure out what the critical F value is for us to reject the null hypothesis. If this F score gets big enough, meaning that the between group variability is a lot bigger than the within group variability, then we're going to reject the null. We're going to say that we think that these group labels actually are meaningful. And again, just like all these tests, F has some kind of parameters that we have to set. The F distribution actually has 2 degrees of freedom, one for this between group and one for the within group, right? And we've talked about this. So the between group degrees of freedom here is k minus 1. The within group is n minus k. And so we need to know both of these numbers to figure out what the right F distribution is. And so usually when people write this, they'll write the between one first and then the within first. So if you see like F5, 25, that means that that's the DF between is 5 and within is 25. Generally, also the between is going to be a lot smaller than the within, right? Between, remember, is k minus 1, where k is the number of groups, and DF within is n minus k, where n is the number of subjects and k is the number of groups, right? So usually df within is going to be a lot bigger. And so then we can, right, if our f is big enough, then we can reject the null, meaning that, right, there's, for any particular f distribution with these degrees of freedom, it's going to tell us how big this f ratio needs to be for us to reject the null. I see a couple of really good questions in the chat. So one is, what if only some of the groups are meaningful and others aren't? This is a really good question that the ANOVA is really bad at answering. So the null hypothesis for testing is that every group is meaningless. So if even one of the, right, if there's, say there's 5 groups and one of them differs from the other 4 and the other 4 are all the same, we're still going to be able to reject the null hypothesis here, right? So the ANOVA doesn't actually tell you which group is driving the difference. We're going to talk in, I think, next Thursday about how to interpret these ANOVA results. So if we reject the null, all that tells us is that at least one of the groups is different, is meaningful. And so you'd have to actually do what we call post hoc tests, meaning after the ANOVA is done, we have to do these other kinds of tests afterward to try to figure out which group actually drove the response. But yeah, at least for the stuff we're talking about today, we can't say anything about which group is doing things, just that the group label in general is helpful sometimes, or at least at least one of the groups is useful to know. Yeah, this is a really good question. This is like a very common problem with dealing with ANOVA results, is that it doesn't actually tell you which group is doing things. It's just testing this very sort of extreme null hypothesis that every group is meaningless. Yeah, there was also a question about N and NT. I'm using them kind of interchangeably. Yeah, NT just means total across all the groups. If I write N, that also means total across the groups. If I'm ever writing N sub I, like in this equation here, then I'm talking about the number of people inside a particular group I, right? So N sub 1 is the number of people in group 1. But yeah, N or N sub T means just how many people are there total across all the groups. Here's what the F distribution looks like. So again, there's 2 parameters to the F distribution: this between group degrees of freedom, which is listed as D1 in this plot, and then the within group degrees of freedom, which is D2. And so it has kind of a like funky shapes for when the degrees of freedom are really small. But usually the degrees of freedom we're using are going to be a bit, hopefully more than a few at least, especially for D2. And so at least for the F distributions that are useful for ANOVAs, they're going to kind of look like either these green or blue or gray things here. Where they have a peak, which is basically between 0 and 1. And then they have they're positively skewed out here. And so just like for the chi-square distribution, we only do one-tailed tests for the F distribution, right? All we're testing is whether there's some relationship between the group labels and the responses. That can't be, that the answer to that is either like there's no relationship or there's a relationship of some strength. There's no there's no sense in which you could have a negative relationship. If the degrees of freedom for the F distribution get really big, which is like this gray plot here, then this actually becomes a normal distribution. And so you sort of see there, this ends up becoming a normal distribution that's centered around 1. For smaller degrees of freedom, it's not really very normal. It's this like weirdly skewed thing that only exists on the positive numbers. So again, the logic here, just like all of the tests we've talked about for the last few weeks, is that we can write down our degrees of freedom, which depend just on the number of subjects, and they depend on the number of groups. That gives us this null sampling distribution for the F statistic. So, right, this tells us that if there is no relationship between the groups and the responses, then these are the F values we should get. And then we can look at the actual F value that we're measuring in our real data and see where it falls in this plot. See how much of the area of this null distribution is even is more extreme than our real data. And that'll give us a p-value, right? That'll tell us what's the chance of getting an f value at least this big if the null hypothesis is true. Right, I'll do one more quiz here. Again, if you have questions about anything, feel free to ask at any time. I can answer them after quizzes too. Okay, so to reject the null in ANOVA, what do we need to compute? So we reject the null if our MS between, our mean squares between, is above some critical value, if our f is above some critical value, if our f is below some critical value, or if our f is above the null hypothesis of 1. All right, you can go ahead and respond. Okay, so yeah, the correct answer is B here, right? We're gonna compute some critical f value from our distribution. Yeah, D is close, right? So the null hypothesis here is that f is going to be about equal to 1, but being just a little bit more than 1 might not be impressive, right? So right, so for example, like with this gray distribution here, right? This is for at least one. This is one particular f distribution, and so right, you can see that right, this is the null distribution. This is telling us that if the null is true, f will be about 1. Sometimes it will be bigger than 1. It usually won't be bigger than 2, for example, right? So for this this gray distribution, our critical f would be like 1.75 or something, right? So yeah, so the f critical, it's going to depend on these 2 degrees of freedom, and we want to get an f score that's at least that big. The mean square between is part of the f score, but we don't actually write down the distribution for the ms between. It actually has a chi-square distribution, but we're not using that directly in the ANOVA. Right, what really matters is this ratio between ms between and this ms within. Okay. So just to summarize what we're doing here with these ANOVAs. Right, so the way we conduct ANOVA is first we figure out the mean overall for the data as well as the means inside each group. And then we're going to compute this within group and between group sums of squares. So we're going to measure how far the between group one, right, is a sum over the groups. How far are these group means from the overall mean? And the within group one is a sum within each of the groups, right? So inside each group, how much variability is there around that group's mean? In practice, to get that within group one, usually we'll just subtract the between from the total, but you could also just compute it directly. Once we have these sum of squares, these SS values, we can then convert them into MS values by dividing by their degrees of freedom. And then we can take a F ratio, a ratio of the mean squared value for between and mean squared for within. This F is then going to be the statistic that's describing for our particular sample how much variability is there between the groups compared to within the groups. And we can compare that to a null F distribution, which tells us what kind of F statistics we should be getting if the null hypothesis is true. And so, again, this is following this general null hypothesis framework. We're computing some kind of statistic on our data. In this case, the statistic we're computing is a little complicated, right? It involves a few different steps, but we compute the statistic on our data, which in this case is an F statistic. And then we're going to compare it to a null distribution of that statistic. So what would that statistic look like if the null hypothesis is true? And again, the null hypothesis here is that the group labels are completely unrelated to the responses that we're getting from people. Then we can compare the statistic we got in our data to this null distribution to see is the F that we got in our data surprising or not? Does this F look like an F that we could get if the null hypothesis is true? And if our F value is really big, then that means that, bigger than our critical F value, then that means that we're going to reject the null hypothesis. We're going to say, it looks like this sample we got has an F score that you wouldn't usually get from the null distribution. So this procedure we've described is called a one-way analysis of variance. And so the assumptions, again, we're assuming these are random independent samples, that we're getting this scale measure from each person. We're also assuming that we're getting some kind of group label from each person. And and we're assuming that every person is exactly in one group. The one way from the analysis in the title of this test is saying that there's a single nominal label that every person has, right? So we're getting two things from each person. We're getting some kind of scale measurement, and we're figuring out which group they're in, right? We have a single nominal factor with k levels, and each person is exactly in one of these levels. So the one way here is meaning the same thing that it did in the one-way chi-square test, right? That there's a single nominal factor. It can have multiple levels in it, right? But there's from each person, we're just getting this scale measure, and we're getting this single nominal measure. There's also some other assumptions that are baked into this null F, getting this null F distribution. One of them is that the within group residuals, which means that the variation inside each group looks like a normal distribution. And the second is that these within group residuals have the same variance. So every group has the same amount of variance inside it. One reason this assumption is happening is because we're just adding up the variability inside the groups. And if the groups don't have the same variance, then just adding those things up doesn't make that much sense. So we're going to talk on Tuesday about some ways to try to get around these different assumptions, right? But at least for the version we're talking about today, it's making both of these assumptions, that each individual group has a normal distribution with the same variance, the same population variance. And so the grouping variable here, again, just like in the chi-square test, is a factor and may have multiple levels. And so, so for example, these levels might be different doses of a drug. So we might have, so for each person, we're assigning them to one of three different groups. And then we're measuring some kind of outcome of, how much does it seem like this person improved, for example. And then our null hypothesis here would be that these groups are meaningless, meaning that whether the person gets the placebo or 1 milligram or 10 milligrams doesn't have any impact on their outcomes, right? There's just as much, even if I knew which group people are in, it doesn't actually help me decrease my uncertainty about what their outcome is going to be, right? And so again, this one-way analysis variance is that we have a single factor. It could have more than two levels in it, right? But every person is in exactly one group. And we're testing to see whether that group has any impact on their responses. And so at least the most straightforward way to use ANOVAs is that these groups are things that we are assigning people to, right? So we're taking people and randomly putting them into one of these groups and then measuring their responses. These groups could also be something that we're asking people, and that's also fine. It's fine to run the ANOVA that way, although again, we have to be a little careful in that case about making causal claims, right? So if these drug levels are things that the individual subjects get to pick, then we might still be able to say that their drug level is related to their outcome in some way, but determining causation could be a little tricky, right? So for example, it's actually often the case that higher, more extreme drugs and higher levels of drugs might be associated with worse outcomes, just because people that are sicker are going to tend to try to take more medication, right? So if we want to make a causal claim about the impact of the drug dose, we would want to assign people randomly to these groups. Okay, so this wraps up one-way ANOVAs. We'll do one more quiz here, right? And so we use a one-way ANOVA when we have scale measures labeled with one nominal factor, meaning that for every person we have a scale measurement as well as a label of a group label. A one-way ANOVA is for a one-tailed test. A one-way ANOVA is used when we have a single group. Or one-way ANOVA is used when we just have a single data point. All right, what do we think? Okay, so yeah, the correct answer is A here. That right, this is the case where we have a scale measurement for every person, and we also have some kind of nominal factor for them. Right, that's what the one way in the ANOVA is referring to. It is B is a slightly trick answer because we are also doing a one-tailed test here in the sense that we are the ANOVA is only testing for some relationship between the groups and the outcomes. There's no sense of a positive or negative outcome. But that's not what the one way in the ANOVA means. And we're going to see in a second other kinds of ANOVAs that are not one way ANOVAs that and they're also one-tailed tests in that sense. If you only have a single group, we would that's what we'd call a one sample test, like a one sample t-test. Right, one way ANOVA is referring to the fact that we have one nominal factor, just like a one-way chi-square test, right, is referring to the fact that we have one nominal factor. Okay, so we're going to talk today about another kind of ANOVA, in which what we talked about so far is an ANOVA for understanding the effect of one factor, meaning a single grouping variable. But we might also care about the contributions of multiple factors at the same time. So for example, imagine that for each person, we have some kind of scale measure of some health outcome, and we know two things about these people. We know what drug dose they were randomly assigned to, and we know their reported gender, right? So now we know two different things about these people. And what we want to know is, first of all, we want to know whether there's some impact on people's outcomes that's related either to their drug dose or to gender. And it might also be the case that there's some kind of interaction between these two things, right? So maybe in order to predict your health outcome, we need to know gender and drug dose at the same time, and we need to make some kind of prediction that's actually specific to a combination of those things, that we can't just know, right? We can't just add up sort of a separate contribution from gender and dose. And so when we're interested in these kinds of questions where we have multiple nominal variables that we have measured in each person, then we can use what's called a factorial ANOVA. And the factorial just means that it's looking simultaneously at combinations of multiple factors, right? So a one-way ANOVA means that we only have a single factor measurement, right? That we only have a single kind of nominal grouping per person. This factorial ANOVA land, now we know two or more, right? We could maybe know 3 or 4 or 5 different things about each person, right? And what that basically means is that we want to know which of these kinds of grouping factors are related to our outcome. So before we were taking our SS total here, which is the total sum of squares, and we were splitting it up into a within group piece and a between group piece, right? So for the one-way ANOVA, there was only one kind of group, right? There was only one grouping variable with k levels, and we could split up this SS total into a within and between group piece. And so in a two-way ANOVA, now what we're going to do is we're going to subdivide that SS between part, and we're going to split it to figure out which groups specifically, right, which grouping factor is actually, we want to know whether knowing a specific one of these grouping factors is changing the sum of squares. And so we can draw a diagram like this. So a couple things have happened here. So one thing is that we're renaming SS within to SS error. That doesn't really mean anything. That's just usually the terminology we use with factorial ANOVAs, but it's the same thing. It's asking how much variability is there that's that even after we know all of the grouping labels of a particular participant, how much residual sum of squares stuff is there. So you could call that within group sum of squares. You could call it the error residual, right? It's just the unmodeled stuff that isn't related to any of the grouping factors that we measured for these people. And then on the bottom part, we've now split up SS between into 3 different pieces. So in our example, for if we know both gender and dose for every participant, we can take this SS between and break it up into how much of the variability in our data is explainable based on this gender factor, how much of the variability in our data is related to the dose that people were put on, and then there's this third somewhat mysterious piece, which we will talk about a little bit today, and we'll talk about on Tuesday as well, which is the interaction between the two of them. And so what this is basically saying is that there's like 3 ways that these nominal variables might impact people's outcomes, their medical outcomes. One is that there may be a different outcome depending on your gender. There may be a different outcome depending on the dose you were put on, and there could be a different outcome based on some combination of those 2 things. And so, so the interaction here is an interaction between gender and dose, which again means that there's something that different doses are working differently in different genders. And so right here, if we have, if people are reporting based on 2 genders and based on 3 dose levels, then that allows us to compute these degrees of freedom in these squares. These degree of freedom things I'm writing out here assume that there's an equal number of subjects in all of the conditions. So for every dosage level and for every gender level, we have the same number of people. If that's not true, then the degrees of freedom get kind of messy. Again, for these factorial ANOVAs, you're not going to be asked to ever do them by hand. You're just going to do them in R. Okay, so just some reminders here, right? So the total sum of squares hasn't changed. The size of the circle is still the same. And the terminology here in these new pieces we've put in the SS between part, the pieces that are related directly to a group are called the main effects. And so right here, we're one hypothesis we're testing is a main effect of gender, meaning is there an overall difference in outcomes between males and females? We're also testing a main effect of dose, asking whether there's an overall difference in outcomes of people that got placebo or 1 milligram or 10 milligrams of drug. And then there's this last bit, which is this interaction effect, right? Which is asking whether is there some kind of difference that's specific to a combination of a gender and dose. So this particular diagram is for a 2-way ANOVA, meaning that there's 2 factors. Again, the general term here is factorial ANOVA, which could be any number of ways. 2-way ANOVA is that there's 2 nominal factors. You could also have a 3-way ANOVA, a 4-way ANOVA, and so on. And so what we're testing here is 3 different null hypotheses, right? We're testing whether gender has an impact, dose has an impact, and whether their combination has an impact. And each of these 3 hypothesis tests, we're going to test, it's basically the same setup as the 1-way ANOVA, right? We're going to compute some kind of mean squared term. We're going to compute some mean squared terms, and we're going to compute an F ratio, and then use an F distribution to figure out if there's any relationship between a group or a combination of groups and an outcome. Okay. So based on what we just talked about, right, a factorial ANOVA is used when we A, have uncertainty in our labels, B, have scale measures that are labeled with multiple nominal factors, C, we can't compute the total sum of squares, or D, we have a small number of subjects. Okay, so what's the definition of a factorial ANOVA? Yeah, so the correct answer here is B, right? Is that we have a scale measurement. Usually it's going to be from each person. We have a scale measurement, and then we also know more than one kind of grouping factor for each person. And so, again, these could be groups we randomly assigned people to, like dose. It could be groups that they're reporting to us, like gender. It could also, these nominal factors could sometimes be like outcome measurements. So we could, maybe we have, we're categorizing people based on some kind of nominal outcome, and we want to know whether it's related to some scale measurement that says something about them, like before we started treatment. Right, but the idea is that we have multiple grouping factors and some kind of scale measurement, and we want to ask whether there's some relationship between this scale measurement and at least one of the grouping factors, or maybe some combination of them. So we're testing 3 null hypotheses here, right? The first one is in a two-way ANOVA. We're testing 3 null hypotheses. One is the main effect of our first factor, which was gender in this example. And the null hypothesis is that knowing this gender group doesn't help us predict your outcome at all, right? The mean outcome in the males and the females is the same. The second null hypothesis is for our second factor, which in this case is dose. And again, this is kind of the like extreme null hypothesis, which is that all 3 groups are identical. So the population response to any dosage of this drug is the same. And so this, if we reject this null, all it means is that at least one of these groups is different from the other 2. And then there's this third null hypothesis about this interaction. And we're going to come back to this in a couple of slides, and we're going to talk more about this on Tuesday too. But this interaction is a very complicated null hypothesis, and like a very sort of strict null hypothesis, which is that we can predict any combination of groups just by knowing the effects, these main effects, right? So the interaction is basically saying that the main effects are all that's going on, that maybe there's some difference between males and females. Maybe there's some difference depending on dose. But the combination of those 2 factors is just the sum of those 2 effects. So we'll come back to this, but right, this null hypothesis I'm writing out here is the hypothesis that there's no interaction, right? So we're testing 3 null hypotheses. There's no main effect of the first factor, there's no main effect of the second factor, and there's no interaction effect between the 2 factors, right? So we're testing with this factorial ANOVA, we can test all 3 of these null hypotheses, and this will tell us something about which of these factors are actually important. So again, you're never going to have to actually like do the math on this, but just to give you a sense for how these tests work. So if we want to test one of our main effects, we again do this pretty much the same way we did in the one-way ANOVA. So we compute the sum of squares of the error term, which we used to call the within group term, right? But this is just sort of like how much variability is left within our data, even after we know all the group information. And we can also compute this mean squares for this gender term, which is how much variability in our data is related just to this gender term, right? So if you look at our pie here, right, we're sort of comparing like this part of the pie to this part of the pie. We're normalizing by these degrees of freedom, right? So we're really comparing are these mean squares. And so we compute this F ratio, which is how much variability in this data is related to this gender label versus just the residual stuff that we can't explain in our data. And this is our statistic we're measuring on our data. And then we can get out what a critical value would be based on our null distribution of what should this ratio look like if gender has no impact on people's outcomes. And so if we get a big F ratio for gender, that means that there is a big impact on people's outcomes from their gender, right? That we can explain, if this ratio is big, it means that we can explain a lot of the variability in our data based on this gender label. And so if this is true, if this is really big, then we would reject this null hypothesis, right? And so oops, that's the same slide. Okay. And so, so if we reject this null hypothesis, that means that we're saying that there is some impact of gender on people's outcomes. We could do the same thing for the dose, right? We can compute this SS dose term here, right? How much of the variability in our data is related to the different dosage that people were put on. We can compute an F-score for dose and see whether it's bigger than some critical value. If it is big enough, then we'd reject the null hypothesis that the drug dosage doesn't matter, right? We would say that it does seem like there's some difference in outcomes depending on which drug group people are in. Again, it doesn't tell us which group is different from the others. It doesn't. So it could be that placebo is different from 1 milligram and 10 milligrams. So just getting any of the drug matters. Maybe only 10 milligrams is different from placebo and 1 milligram, meaning you need more than 1 milligram for effects to kick in. Again, we'll talk next week about how to actually figure out where these differences are. In practice, also, it's really helpful just to have visualizations of your data, right? If you just visualize the means of the data in some way, that can help you figure out what group is actually driving these differences. Okay, so this is for main effects, right? So we can compute, there's two null hypotheses we're testing there. And then there's a third null hypothesis here, which is testing interaction. And so the math here is identical. We just compute this SS interaction term, which again, we're not going to talk about how to actually compute, but this is basically the variability in the data that's explained by some kind of combination between gender and dose. So it's basically saying that if we know your gender, does that give some overall boost to your outcomes? If we know your dose, does that give some overall boost to your outcomes? And then it's asking whether there's some kind of predictable change in your outcomes that's on top of that, that's related to the interaction between these two things. And so the math here is identical. We just compute this mean squares. We compute our F ratio, and then we look to see if this F ratio is really big. And if this F ratio is big enough, it means that there is some kind of interaction in our data. Right, so for testing each of these hypotheses, it's like the same setup. We just need to know these sum of squared things. We need to know the degrees of freedom, and that lets us compute these Fs. Right, and to figure out our F critical, that we also need to use the degrees of freedom to figure that out. So the most complicated part of these are these interaction things. So just to give another example of what this means. So if there's no interaction in this example, so let's imagine that there is some kind of gender effect and there is some kind of dose effect, but there's no interaction. And so what that means is that there's 6 different categories of people in our experiment, right? There's 2 levels of the gender factor times 3 levels of the dose factor. And so what that would mean is that those 6 groups can be modeled by just knowing 4 numbers. So one way to break this up would be that we know what the mean outcome is for females that were given placebo. So that's kind of like our baseline condition. There's some kind of gender effect. So there's some difference in outcomes between males and females that we're modeling. And that's right. If the main effect is significant, it means that this thing is different from 0. And there also we're assuming here there's a main effect of dose, meaning that at least one of these 2 numbers is non-zero, right? Either that if you go from placebo to either 1 milligram or 10 milligrams or both, there is some kind of non-zero effect on people's outcomes, right? So these are 4 different numbers. There's a baseline condition. There's a gender difference here, and then there's 2 potential dose differences, right? There's 3 total levels of this dose, so there's 2 values here. And so if there's no interaction, what that means is that for any one of these 6 groups, we can just add up the gender and dose effects. So for example, if we wanted to figure out the mean outcomes of males who are taking 1 milligram of the drug, what we do is we'd start from our baseline condition, which is this female placebo condition. We'd add in the gender effect. So, right, what's the difference in outcomes for males versus females? And we'd also add in this dose effect, right? So if we switch from placebo to 1 milligram, how much does that change outcomes? So if there's no interaction, then this equation is true, right? That we can predict any of these combinations by just adding up these individual main effects. If there is an interaction, then it means that this equation is not true, that maybe men taking 1 milligram of the drug do like really, really poorly, right? If that's true, then it means that that's not really a gender effect and it's not really a dose effect. It's a combination of the two of them, right? That this specific combination is really bad for some reason. And so that's what this interaction hypothesis is testing is, can you actually just add things up like this? Or do we need to instead know for each of the 6 groups, there's some kind of group specific mean, right? The interaction is basically asking whether can we get away with only 4 numbers here, right? These 4 numbers to explain our 6 means, or do we really need to know all 6 groups, right? Do we really need 6 numbers, 1 for every group, in order to model the ways that these means are different across the groups? Okay, so as a quick test here, how many null hypotheses can we test with a 2-way ANOVA? 1, 2, 3, or 4? Oops. My timer is not working. I'll just count 10 seconds in my head here. Okay. So what do people think? Yeah, so the answer here is 3, right? We can test a 2-way ANOVA means there's 2 factors. So we can test a main effect of one factor, a main effect of a second factor, or the interaction between the 2 factors. So if we think about, for example, a 3-way ANOVA, the number of null hypotheses we can test actually starts getting a little bit crazy, right? So a 3-way ANOVA, there's 3 main effects we can test. And then there's 3 2-way interactions. It could be interaction between factors 1 and 2, or 1 and 3, or 2 and 3. And there actually also could be a 3-way interaction between all 3 factors, right? So these factorial ANOVAs start being able to test many, many null hypotheses, and we'll talk more about this on Tuesday as well. Okay, so to sum up this 2-way ANOVA, so the assumptions here is all the same stuff as the 1-way ANOVA. So these are random samples. Each group has the same variance and is normally distributed. Every participant belongs to exactly one level for each factor, right? So we know multiple things about each person, but each person is in exactly one group for each of the grouping factors. We're also assuming that the contributions of these factors are additive, and what that means is that at least for the main effects, right, that these have for the main effects, we're testing that these have additive effects. We could also, if things are not additive, we can also add in these interaction terms, right? But even for the interactions, we're basically assuming that these are on top of these additive effects. And so any variability that's related to these additive main effects are going to be that's related to these additive effects for each factor independently are the main effects. Anything that's still explainable but requires you to simultaneously know multiple groups are the interactions. And anything that we can't explain based on these group levels is the within group errors, right? So errors here means that even if you simultaneously know all of the grouping information for this person, there's still going to be some residual amount of error in predicting their outcomes. So we refer to this as an omnibus test. What that means is that it's simultaneously testing a bunch of null hypotheses, and each of these null hypotheses themselves is also kind of complicated, right? So for example, for the main effective dose here, we're testing we're testing really three null hypotheses. We're testing that placebo equals 1 milligram, and placebo equals 10, and placebo and 1 milligram equals 10, right? So this means this is an omnibus test, meaning it's like testing lots of things at the same time, which in some senses is great because it means that it's a quick way to test whether there's some relationship between our groups and their outcomes. It's bad because it means that the p-value we get doesn't actually tell us why these null hypotheses were false, right? Which of these equal signs is not true. And so we need some more advanced tools to actually figure out that part, which we'll talk about next week. So interpreting the result of two-way ANOVAs is like a notoriously challenging thing that even statisticians still argue about to some extent. So if you get only main effects out of an ANOVA, meaning only the main effects are significant, then this is not that bad. So if we have let's imagine we have an experiment where we're measuring from each person, we're getting some measure of conscientiousness. So this is our scale measure we're getting for each person. And we also have them report their gender, and we have them report political affiliation, where both gender and political affiliation are some kind of nominal outcome. So if we run an ANOVA and we find that there are, for example, say there's a main effect of gender but not political affiliation, and there's no interaction, right? What this tells us is that there's some difference, some gender-related difference here in this outcome. There wasn't a politics-related difference, and there wasn't any kind of weird combination where, so people that are identifying as Democratic women, for example, don't have some kind of specific conscientiousness score. But when you get these interactions, it can be a little hard to interpret what this actually means. So, for example, let's say there's main effects of gender and political affiliation and interaction. That basically it doesn't tell us anything about how conscientiousness is actually different. It just says that there is some kind of significant pattern here, right? That the combination so there's some overall difference in conscientiousness across gender. There's some overall difference across political affiliations. And there's also some gender affiliation combination specific conscientiousness scores. But it doesn't, right? Just the ANOVA itself doesn't tell us anything about which scores are higher and lower. So in order to figure that out, first of all, you could use some kind of visualization of the means. So if we can plot the means in some way, that would help. We can also run what are called post hoc tests, which we'll talk about next week, that can help us pull apart which groups actually differ from which other groups here, right? Why were these significant? Which specific groups are driving these differences? And so, this basically just means to be a little bit cautious about interpreting ANOVA results, right? That whenever we're running an omnibus test like this, it means that these null hypotheses are kind of extreme. The null hypotheses mean that all of the groups, the levels of the group are the same. And so if we reject that null hypothesis, that it could be rejected for many reasons, and we need to dig in to figure out what those are. Okay, so to sum up, this ANOVA, this analysis of variance test, lets us compare the means of more than two groups. We do this by computing this F ratio in our sample, which tells us something about how much variability there is across groups versus within groups. And we can compare that F ratio to a null distribution. We can do this as either a one-way ANOVA, meaning that there's a single grouping variable, as well as a factorial ANOVA, meaning that there's multiple grouping variables. And with these factorial ANOVAs, there are both main effects of groups as well as interactions, meaning that there's some kind of non-linear, non-additive outcome that's coming from combinations of different factors. All right. Any last questions? All right, so just as a reminder, So at this point, you know all the material for the lab, which I'd encourage you to do today if you can. There's a homework due next week, which again is also based on this material. The TAs will be holding their like lab office hours during their lab times today. You can also contact any of us if you need help outside those times. Great. I'll see everyone next week.